Welcome back to Disputed and Multi-GPU Deep Learning. For these videos, we'll be talking about how we can do disputed training using TensorFlow and Keras. So we're going to do a deep dive into disputed training with TensorFlow. So disputed training with TensorFlow. So in the easiest scenario, a single CPU with multiple cores is actually enough to support the training. Keep in mind that we can also take advantage of the multi-threading. So if each core has X number of threads, if you have two cores, we can have 2 times X number of threads running. To speed things even more, we can add a GPU accelerator and we can transfer our data and gradients back and forth between the CPU's memory and the GPU. So what the GPU is basically doing is to accelerate the mathematical computations, especially large vector multiplications and matrix multiplications is something which the GPU can do a lot faster than what we can achieve with the CPU alone. That's because the hardware of the GPU is actually designed specifically to accelerate certain operations such as matrix multiplications, because that's the same kind of operations that we often need to do to render graphics as well. Now the next step is to actually add multiple GPUs and to finally have multiple machines running multiple GPUs on each one, all connected over the network. So we're going to look at stepping up the parallelism from just one single CPU to multiple and one single GPU to multiple GPUs, and finally multiple GPUs over multiple machines. And here's some terminology. A worker is a separate machine that contains a CPU and one or more GPUs. So a worker is a node or a machine that contains a central processing unit, a CPU, and one or several GPUs. Then the accelerator is basically the GPU, or what is specific to TensorFlow by Google, called the TensorFlow Processing Unit. It's an AI accelerator. But it's not a graphics processing unit being used in that way. And finally, all reduced, and this is actually a synchronization algorithm that does distributed synchronization in a ring-like fashion. This is a distributed algorithm that aggregates all the trainable parameters from different workers or accelerators, and essentially it receives the weight from all workers and performs some sort of aggregation on them, computing the final weights. So talk about this distributed synchronization algorithms as we go along. So there are actually two different distributed training strategies. We can roughly distinguish the strategies into basically two big categories: synchronous or sync and asynchronous. In synchronous training, all the workers and accelerators train over different slices of the input data and aggregate the data gradients at each step. So they need to synchronize with each other, right? So that they have a similar notion of the model after each step. And in asynchronous training, all the workers are independently trained over the input data and update the variables in the asynchronous manner, like using the all reduce. So this is a different way of doing the training. Obviously, synchronous is slightly more easier to perform, but there are some limitations when the network grows beyond a certain size. So asynchronous is more popular where the network is larger. So in synchronous training, we send different slices of the data to each worker. Each device has a full replica of the model and is trained only on part of the training data. So this is actually essentially a data parallel model, right? So there's a replica of the model in each GPU. So this is a data parallelism at work here. And we are sending different slices of the data, training data to each of the workers. The forward pass begins with at the same time with in all of them. They all compute the different outputs and different gradients. So the forward is actually sent to the output layer. For each of the nodes, this actually occurs independently. At this moment, all the devices are communicating with each other and they are aggregating the gradients using the all reduced algorithm. When the gradients are combined, they are then sent back to all the devices, and each device then continues in the backward pass, updating the local copy of the weights normally. The next forward pass doesn't begin until all the variables are updated. So there's a synchronization occurring here. So we update the forward pass on each of the nodes. We update the gradients that's being calculated here. Then we need to do some combination because every single node will have a slightly different error or loss because they're each trained on different slices of the training data, right? So we need to do a combination to synchronize a global picture of the loss function, and then the gradients are sent back to each of the different nodes, and then we do the backward pass. We're updating the local copy of the weights because the weights in each of the devices are different, so we update the weights with the common set of parameters. At each point of time, all the devices have exactly the same weights, although different gradients because they've been trained on different data. So that at any time we need to basically update that information about the weights so that they are synchronized with each other. They have their local copy, but the values should be the same because it's actually supposed to be copies of the same neural network. However, as mentioned here, because they are being trained on different slices of the training data, they will actually generate different gradients at the output layer because actually the input is different. And once we have updated this information, we then try to update all the hidden layers according using backpropagation such that a common replica is actually maintained in each of the different layers. In TensorFlow, this is actually referred to as a mirrored strategy. So it's actually for data parallel with multiple GPUs, and there are actually two different types. If there's only one machine with multiple GPUs, then we would just use the plain mirrored strategy. This is designed to run on multiple GPUs on the same worker, the same node. While a separate one called this multi-worker mirrored strategy, this is actually used for the case where we have multiple CPUs or multiple nodes, as well as multiple nodes or multiple workers, as well as multiple GPUs on each of those. The basic principle behind the two are actually the same. It's actually how they synchronize or update the gradients into the different GPUs or replicas of the model that is actually different. So obviously, if it's on the same machine, it's a lot simpler. But if it's on multiple machines, then they need to work out a scheme to actually transmit this information over the network. Whereas if it's on the same machine, it can be basically copied over the same computer bus. So there's no need to transmit over the network. So this is called the mirrored strategy. Every variable in the model is mirrored across all the replicas. So this is data parallelism. So there's a replica of the model in each GPU. So together, these variables form a single conceptual variable called the mirrored variable, hence the name mirror strategy. These variables are kept in sync with each other by applying identical updates. So this is part of the syncing process. We need to make sure that the variables are kept in sync by doing an update, a global update that actually updates all copies with the same values. Now, each of the gradient being calculated by each of the node would be different, but we do this syncing step to make sure that we merge those values, and then we use that merged value to update each of the replicas with the same values after applying the gradient descent to it. Now, the initialization strategy for this is just to create the mirror strategy using TF distribute mirror strategy, and you need to specify the devices that you're going to be using. So we will have two replicas, one on GPU 0 and one on GPU 1. Now to train, we just need to use with mirror strategy.scope and then put in the model, do a compile and fit. And all the magic actually occurs behind the scenes when you use this mirror strategy scope. This scope actually makes sure that all the variables are mirrored to all the devices, and underneath this, the values are actually updated and make sure that they are all the replicas are having the same values. This is important because although we have it separated out into different GPUs, the same variable into different GPUs, they are supposed to be the same mirrored variable and hence should have the same values. Otherwise, at the end of multiple iterations, you will find that each GPU is maintaining its own version of the neural network and they are not exactly the same. And then it will be not possible to actually merge it together. So at the end of each iteration, as mentioned in the previous slide, we need to do an update step to make sure every GPU has the same information and then continue the training from there. And you have to do it at each iteration so that it doesn't go further and further apart. So this is actually a graphic to represent what we were talking about in mirror strategy. We have one single worker, one node with a CPU, and then in this CPU we actually happen to have multiple GPUs, 0, 1, 2, and 3. Now it is possible that you only use 2 of them, even though physically there are 4 GPUs, like the example previously. So the TensorFlow code will be running in the CPU, and what it does is that it will make copies of there's actually a back and forth, right? The memory of the CPU is being copied to the GPU in order to do the arithmetic, right? The mathematical computations. And those variables that are mirrored, they are copied over to each of the mirrored strategy GPUs that you configure. So if I have I have one model that was running just now, and I'm using GPU 0 and GPU 1 at the part that I use the mirrored strategy scope, it will start copying out those variables that are in both the compiled model into GPU 1 0, and also make a copy of the variables to GPU 1 as well. Now when it calls fit, this is when the magic happens, right? When it does the gradient descent, we call fit. It's going to run through each mini batch of the data with the individual GPUs, and because they are using different mini batches, actually these values may be different at the output when it completes. So each of these will have this slightly different output and also different gradient with respect to the loss function. So these two output values will be different because with respect to the gradients with respect to the loss function will be different for each of the GPUs. So the information needs to be sent back to the CPU to do a synchronization process. So the gradients needs to be updated for both of them, and then this value will be actually once you have a global copy, right? This information will be then used to actually do the back propagation, all within the fit function, right? The back propagation for each of the respective neural net. So you find that actually the synchronization has to happen at the end of each iteration. It is not even the end of the epoch yet, right? So you may be training it for 100 epochs. Within 100 epochs, you may have 10 iterations. So at the end of each iteration, when the gradients are computed, that is when you need to synchronize the gradients, because even though the two values are different, you cannot just use it independently and start updating the weights, because originally the weights are the same. They are replicas of each other. But if you apply different gradients in the fit function, then each of them will have different weights being updated. So we need to synchronize the gradient values being computed so that when we do the update, it will be updating to the same values for both of the neural network replicas. Okay, so that's basically what happens in the background in those few lines. This is very simple. It's just like 3 or 4 lines of code, but a lot of things happens in the background which is actually being accomplished by the TensorFlow distribution strategy. In this case, the mirrored strategy. And mirror strategy is actually used for this kind of configuration where you have a single server, one or more CPUs, doesn't really matter. This is just a virtual representation of a CPU, but one single group of CPUs, and each of the GPUs are running independently. So there are multiple GPUs on the machine. Now, if you need to have faster speed in computing, you can use each of the GPUs available. So during the initialization, you can initialize it to use 4 GPUs instead of just 2. And the mirror strategy will then replicate the data. Instead of just 2 GPUs, it will replicate to all 4 of them. And since the speed now will be sort of multiplied by 4 times, it will correspondingly do the training faster. So this is actually data parallelism. The model is replicated, the computation is spread out. It doesn't actually handle the case where the data is too large to be handled. I mean, the training data is too large. But in a sense, because we're actually using a separate mini batch for each of the GPUs, the data will be actually separated out to the different GPUs anyways, naturally as part of this process. The only thing you need to watch out for is that the mirror strategy needs to take care of the synchronization with more GPUs now, and therefore it will take a slightly longer, but it's just going to be a fraction of a second anyway. So it's all within the same machine, so the bandwidth or the communication path between each of these machines is very, very quick over the high-speed computer bus that we have in most servers. It doesn't go over the cloud, doesn't go over the network, so it's all within the machine. So we are just using the memory bandwidth to communicate between them. So this is going to happen in nanoseconds, right? Very, very, very quickly, and we shouldn't have any issue with the bandwidth. Now, but there is a limit to how many GPUs you can fit within one server. So this mirror strategy is only good enough if your model is not particularly huge, right? It's just that you need more computational power than what is just available on a single GPU. And with that, we come to the end of this set of slides. So thank you for your attention.